Hello, welcome back for the second part of the discussion on the question. So let us see what is asked for here in this sixth question. There is a direct mapped cache which is shown as a picture here. Of course, this is an answer too, but how to arrive at this answer, let us see. What you have to do is, based on the values given, try to construct how many bits are required for each of those things to be accessed. Now it says that the block size is 4 bytes. As you know that cache size as well as block size are powers of 2, and it says that block size is 4 bytes. Each block is block 1 is 4 bytes. That means what? In an address, the lowest portion, the lowest number of bits, bit 0 to whatever, is going to be accessing the block. So when the address is increasing, you know that the LSB will be increasing first and then the higher bits, right? So once you identify a particular block, the next address would be accessing the next byte within the block. So that will be the increase that is happening on the lower part of the address. So always start from the LSB side and then go towards the higher side. So if block size are 4 bytes, that means 2 bits will be required to access the block. So this, whatever the block answer which is given here, 2 bits are required to access a block. Now cache size. Cache size says it is 16 bytes. So the entire cache is 16 bytes. Now it should be the multiples of blocks. Okay, you cannot have a half block in a cache. So 16 bytes, of course, is indirectly tells you that there are 4 blocks in the cache. So block 1 to 4 I have written, so 4. Now if we are not going to have all the addresses contiguous here, okay, each block may be carrying the particular block of a main memory, so it need not be contiguous, but still there are 4 blocks which are to be accessed. Okay, don't worry about the contiguous, whether they are going to hold the contiguous blocks of the main memory. 4 blocks are to be accessed. So how many block IDs, the block index, you need? Again, if you are to access 4 blocks, you need 2 bits, right? Because 2 to the power 2 is 4. So the next 2 bits, which is B2, B3, are required to access the blocks. Okay, so you have to say, you have to reserve that many two bits for accessing the blocks of the particular cache block within the cache. Now let us assume how many total, what is the address bits required to access the entire main memory. Here it says that main memory size is 32 bytes. Again, you know that it is multiple of 2, and you have to divide. You can see that it has got 16 bytes of each block. Okay, block 1 to block 4. Let me say I am writing it 1 to 4, but maybe 0 to 3 is also valid, and then again another block 0 to 3. So that means there are 4 blocks here. Okay, so let me add one more. So 4 blocks here and another 4 blocks here. Okay, so this is 16 bytes. Now totally 32 bytes are going to have exact size of a cache. Okay, how many? See, always remember the main memory should be multiples of cache size. So if the cache size is 16 bytes, I need to have my main memory which is a multiple of cache size, because I need to have the same number of blocks that are there in the cache also on the main memory, so that I can pick up one particular block and then map it to the particular block in the cache. So let me change the color now. Now what happens? I said that it is a direct mapped cache. So each cache, whatever the block 0 is there, is mapped to this one. Similarly, the block 0 of this is also mapped to this. So either this block will be residing or this block will be residing. Now if you need to access this, how many bits are required? There are only two multiples of two cache sizes of thing which is available in main memory. So you need one more bit here, which is either 0 or 1. So if you are accessing the top cache, then it is 0, and if it is 1. So this is called tag. Now, once this is done, your mapping will be easier. Okay, all the top blocks of this will be accessing this, will be mapped to the top block of the cache, and then the bottom of this particular cache will be block will be mapped to this. So basically what we are doing is the cache size and the block size decide the block index and the within that offset. Okay, this can be called as an offset also, block offset. Within the block, how do you want to access it? So these bits can be decided, and then the total memory size, or whatever bits you get, the remaining bits will be here. Okay, so if the total main memory size is maybe 128 bytes or maybe 1024 bytes, you know that it is multiple of the cache. So this is a simple calculation, and this is how you compute the values. Okay. Now let us look at the next question, which is very simple, which has been already explained also in the previous lecture. What is the functionality of the dirty bit in a cache? So dirty bit in a cache, basically, there is one dirty bit maintained per block. Okay, it is not per byte or per word. It's a per block basis. A bit is reserved. One is valid bit, another one is dirty bit. Okay, let me call it as V or D. Now, what is valid bit? See, a cache may be initially empty. It doesn't have any block from main memory which is copied into it. So in that case, you have to, there is some mechanism to say that that particular block within the cache is empty. How would you show that? Because even all zeros, if it is stored, it could be a valid content also. So we need to have one bit to say that that particular block is not holding any content of the main memory. So that is valid bit. Valid bit, if it is 1, that means you have copied some block in the main memory into cache. Now, you could have copied that, but you might have not modified anything. So in that case, if it is a data cache, of course, then we have to say that the dirty bit has to be 0 if nothing changes, no changes have been done since it has been taken from the main memory. Then you need not have to copy back to the main memory if that particular block has to be evicted. So dirty bit is 1, then we say that that particular block is modified, not say corrupted. Okay, it's not that dirty bit doesn't mean that the block is corrupted. Corrupted thing need not be copied back to main memory. There is no corruption we expect to be happening. So it is a changes that is happening to the block which needs to be reflected. But we are calling it as a dirty just to mean that whatever I brought from main memory is modified. It is a valid modification done by the CPU. So when you are evicting the particular block, it needs to be copied back to main memory. So basically, write bits are valid for only data cache, and it is not valid for instruction cache because instruction cache is not going to be changed by the CPU. It is only read and executed, and we don't normally change the instructions. So instruction caches are not having any dirty bit associated with it. So that's the answer for it. So let us go into our 8th question. Now, this is the CPU which we have designed using the CPU sim, and these are the hardware available. This links are there. Now the question is about the R2, which is having a connection. There is a data bus going. Whatever is the content of R2 is going to be given there. But remember the width of those registers. The source is R2, which is 16 bits wide, and MAR, which is the address register, which is 12 bits wide. So it cannot take up all the 16 bits of the R2 content. So what is happening will be, in this kind of scenario, we will be copying some part of the R2 content into MAR. So it depends on whether you are, as per the simulator, we are taking a left offset or right offset. And you know that we will have the content of R2, which is going into MAR is only 12 bits wide. So let me take the answer here, which is R2's content. It is 4 to 15. Actually, we can actually write it in whatever way you want. R2, we need 12 bits to be taken. you can say that 0 to 11 are taken. Okay, that is also a valid answer. Or you say if it is index is from this side, okay, because we have constructed the simulator using that. If the contents are indexed from this side, then 4 to 15 is a valid thing. But basically, this is B0 to B11, which happens to be 12 bits. Either you can take 4 to 15 or 11 to 0. Both are valid in this case. So we have R2, the 12 bits of content of R2 is moved into MAR, because we assume that the address is in R2, which is copied into memory address register, so that you can read from the memory. Now, what are you reading from? We are reading maybe the data portion of the memory. So it is the MAR address, whatever is the content of MAR is put into the memory address bus, and the memory gives you the data at that particular address. Now that is moved, the 16 bits of data, so MAR address plus 1, because it's a byte addressable memory, and 2 bytes, consecutive bytes, we are reading it. 16 bits of data is coming into MDR. So always remember, when you are reading something from a memory, it is addresses to be put in MAR, and it is going to memory. Read or write cycle is performed, and the data flows either from MDR towards the memory or memory to MDR based on what read or write you are doing. So right now we are reading from the memory the content stored at the address which is available at R2, and we gave the offset because R2 is having 16 bits, whereas MAR can accommodate only 12 bits. So we have to extract out 12 bits of the content from R2 and put it in MAR, access the content, take it to MDR. Now data is read, which is 16-bit wide. Now that data has to go to accumulator. It can also go to R1, but I am saying that the move instruction is what you are implementing is accumulator. So the micro instruction has to move the content from MDR to accumulator. So that is what is the third micro instruction. And remember that end is also very important instruction here, because this is not going to be continuous. Okay, we have to inform the simulator that this execution cycle is ended. Okay, it is not going to be continued. So this instruction is done with its job of loading the content of whatever is there, the 12 bits of content in R2 is put in MAR, content is read from the memory, put into accumulator, and that the job is done. So this is what is the required answer for this particular implementation of this instruction using micro instruction. Now let us understand that the question 9 is also similar to this, but we are using the same almost CPU, the similar CPU. Give a set of micro instructions for fetch cycle. Now, as you remember, there are 2 cycles in the CPU in our simulator. First, the instruction is fetch. There are set of operations done to fetch the instruction, which is called fetch cycle. Then whatever you saw for execution of particular instruction, which is execute cycle, which is ended with the end statement. Now let us look at the answer for our fetch cycle. You see that when you are fetching an instruction, the address is pointed to by PC, program counter, which is shown here, PC. So PC to MAR is what is to be done. Now you have to put the address which is available right now in PC into MAR. Once that is done, we are now pointing, this address is pointing at the instruction which is wherever instruction is stored, because this memory is supposed to be holding both data and memory instruction. So that's 12 bit, because both are 12 bits, you don't need to give any offset here. Entire PC can be put in MAR, and then it goes into memory, and it is giving you the instruction into MDR. Now the MDR is having the instruction which is 16-bit wide. Now this instruction cannot go into accumulator, because whatever you are getting it initially comes to MDR. From MDR, it should go to IR, instruction register, because instructions don't go to accumulator or any other registers, so it goes to IR. Then, since fetch cycle should be ready with the next address for fetching the next instruction, here we are assuming that instruction is of 16 bits wide. That means 2 bytes width. So we have to increment the PC by 2. That is also done in the same fetch cycle. Then starting decoding is also done in the simulator in the fetch cycle, because there is only fetch and execute cycle. There is nothing called decode and multiple stages that we have in pipeline. This is a simplest PC simulator CPU we are implementing. So decode also has to be done. But remember that this should not be ended with the end because the fetch cycle is not done. It's not stopping here. Now the simulator is supposed to go into a execute cycle. So we should not put end here because the simulator will assume that we have to stop it here. But the simulation doesn't continue, stop here. After the fetch cycle, execute cycle has to be performed. That is the reason we are having this particular thing. Okay. So I hope this is clear, the fetch cycle set of micro instruction. Now let us go into the next question, which is question 10. Okay. Let us change color. Okay. This I am going to explain you with elaborate diagram. Here, let me first explain how things work. See, we have multiple processors in a system, and we also have a caches which is local to each processor, and there is a snooper circuit, which is a digital circuit giving information about what is happening in the bus. Okay, Snoopy bus, or this is a cache coherence protocol implemented using snooping. So what does it mean? Each cache here not only monitors the transaction happening between the CPU and the cache, also the interaction with the main memory and other caches which are related to the blocks which are available in the cache. See, remember, multiple caches are there. The same address which is in the main memory could be residing in multiple caches. So in that case, any processor performing any operation on those blocks will have an impact on other entries of the same block of main memory in different caches. So how do we know what is happening on other caches? The snooper circuit sitting here will be informing the cache about all the blocks, okay? Whichever blocks available in the individual caches, they will also be mapping to some location in the main memory, of course, and same this main memory blocks, okay, may be residing in the cache on different locations here. They need not be on the same location, but the main memory block, a particular block which is residing in multiple caches, ought to be monitored. Why? Let me give an example to make you understand the scenario. Suppose I have a block here. Okay, one particular block of, that each cache block is mapped to something in the main memory. Now imagine that I have the same block maybe sitting in different locations in the different caches. Assume that this is something about the instruction. Now instruction, okay, this instruction is being, maybe there is a shared library, okay, and everybody is executing maybe printf, and that printf code which is residing in the main memory is being cached into the each of those caches, okay, into all the individual caches. Now what will be happening? What will be the state of this block? If I have to ask you, you should be able to tell this, because there are different states maintained about each block. Okay, please remember the states are per block. Now let me explain what are those different states available. Okay, M is modified, E is exclusive, S is shared, and I is invalid. Invalid means a particular block in the cache. Let me draw the cache on one cache here and a block here. Now invalid means that valid bit is 0. This cache is not mapped to anything at all, this block. So you don't need to worry about this block at all. Now what is shared? Suppose this block is available here. That means it is mapped to a particular location here, and it is here. Now I said that in this scenario, this block is available in all the caches. Okay. Now can you guess, if I say that this is an instruction block, and what will be the state of this particular block in each of those caches? See, remember, the states of each block is local to this processor. Okay, they are all maintained individually, but the block may be here block 0, it may be block maybe 3, and this may be block maybe 32. Okay, this also may be last block, so block 32. So different blocks are there. They could be fully associative or direct mapped or whatever it could be. Now, since it is an instruction cache and the blocks are available in different caches and all of the processors are executing it, can you tell me what will be the access that this processor will be doing on this block? It will be only performing a read operation, right? It won't be performing any write operation on these blocks because it's an instruction block. And what will be the state of these blocks in these caches? You should be able to guess it. It must be in the shared state. Okay. Now, since these blocks are all available in the individual CPUs, every time they are trying to perform a read operation on these addresses, when it is generating this instruction address, it will be seeing a hit. So it will have a read hit and it will be in the same state. There is no need to move the state from shared to anything else. Now, this is the operation done locally. Okay, locally initiated read operation. Okay, if this is performing a read operation. Now, suppose this cache is here, block is there, and then this particular CPU is performing a read operation on this block. Okay, and it will be local to it. So any read operation local will not be reflected on the other caches. So let me show an example, okay, scenario wherein, okay, this block is not there in this cache. Okay, let me give a scenario wherein this block, the same code is trying to be accessed by this processor, but it is not available in the cache. Same instruction is required for this processor also, but it is not there in the cache. Now, it is going to map that particular thing into this particular location maybe, and then it is going to read from this. Okay. Now, it is performing a read operation. It will have a miss now. Okay. Locally, it will have a miss. Where is this map to? Okay, it is invalid, and now internally this cache is not there, so it's a read miss. Okay, now when this particular miss is happening, this read operation is performed. All these individual caches will be, informed about the same block is being accessed by somebody else for a read purpose, and the individual states of these cache blocks are shared, and the other processor is performing a read operation on that particular block, and it will have a miss locally, but these are all accessing it internally, but externally this particular cache is accessing it for a read purpose, and it will be notified that this particular thing is reading it. Now it is for a read purpose. Okay, and we are doing a read operation. Okay, in that case, what happens? Let us assume this operation is performed. Now let us see what will happen when this is performing a read operation on a particular block which is already there in other caches in a shared state. Now locally it will be invalid. There is a miss, so it is a invalid. So locally this particular block is going to be invalid, and it is trying to read memory for a read purpose. So it is a memory read. It could be either this or this. Now memory read is performed, and this particular block is available in other caches. Okay, so that means they are in a shared state in other caches. In that case, what happens is it is in a shared state in other caches. So read miss is happening. Okay, then it will move. It will also move to shared state. Okay, so locally, because of this action, it will move to in the local element, or this particular block may be taken from here, or it would be read from the main memory, but it will be kept in the shared state. Now this also joins the shared state. Now what happens to the remote access? Now this is what is the transition shown for remote activities happening. Now all these caches through the snooper will come to know that some other processor is accessing it for a read purpose. Okay, memory read is performed on the block which I am having it in shared state. If I am seeing that there is a memory read happening on the bus from some other processor, I will continue to hold my particular block in the shared state, because anyway that person is also trying to read it. So I am also reading it. So no problem if multiple people are having the same copy in different caches For a read purpose, there is no harm, and they are in sync with the main memory, so it will be read. So this is how you need to understand the state diagram transition shown here. Okay, so let me erase all. Okay, we are not able to perform. Okay, now how to explain the transition of this? Suppose if this is asked, you know that it is a locally initiated access. It means that I am not having that particular element, and my local processor is trying to access it for a read purpose, and it is in a, it's not available anywhere else. Okay, this block, first time this guy is reading from a particular block from main memory. It is not there in any of the other caches. So it is, if it is that kind of a memory read, then I will take it, this block into this. I am only holding it, so I will make it as exclusive state. And if further reads are happening, I will be doing a maintaining in the same state, because this processor is only owning it. So this is the action done when there is a particular block which is not available. There is a read miss happening, and this is first time this block is being read by the processor, and it will be maintained in the exclusive state, and any further reading happening will be a read hit, and then it will maintain in the same state. Okay. Now, what if this particular transaction is to be explained? Now, what does it mean? I have a local copy which is not any, it is a read miss. Okay. This block is not there in my local cache, so I need to get it from the main memory or maybe from other caches. Now, suppose read miss is happening when this particular block which I am interested in is in shared state in some other cache. Okay, that means what? If it is in some other cache in shared state, then more than one processor is having the same block in some other, in their own caches for the read purpose. Okay, otherwise it would have been in an exclusive state. Okay, so in that case, what I should do? I need to move it to shared state. Not only that, I am holding this particular thing in a shared state, other blocks, other copies of the same block will also be moved to shared state, because they will have to be, now all multiple CPUs are having the same block for the read purpose. Okay, so that's how this transaction is shown. Now, when you are having, suppose, no, I am having it in shared purpose. I already explained you this. Okay, other changes I have already explained in the different cache coherence protocol related video, so you can get it from there. Okay, so let me stop here. This is how you need to understand the behavior of cache and the two transition diagrams that are shown. So what is the answer to be written for this particular thing? You have to say that what are the different states. Modified state means cache line has been modified, is different from main memory. It is the only cached copy that is available in this, and the data bit is set. Exclusive means this is the only cache line, contents are the same, and contents are the same, and this is the only cache which is holding the particular copy. Now the transition means that, okay, in this picture, whatever question was asked, let me show that picture. This transition means that exclusive to modified means that when the processor wants to write into the block which is in the exclusive state, it should be changed to modified state, and it will be different from, the copy of that block will be different from main memory, and the dirty bit of that block will also be set. Okay, so that's how this particular question has to be answered. Now let us look at the final question, which is given here. In a system of, let me take this picture. Now, a system main memory consisting of 256K. Okay, 256K. Now, how many bits are required for 256K? Okay. Let us see why I am adding 16. Okay. Let us start from. Okay, let us understand this question. I made some small changes to the answer key so that it captures exactly there was K missing in the original answer. we had shared with you. Now, look at the question now. Is a system memory consisting of 256K of location. Okay, this is the main memory which is having 256 kilobytes of size. Now, always a simple thing to remember is 1K, okay, kilobyte of locations can be accessed with 10 bits of address. Okay, this is very 2 to the power 10 is 1K, easy to remember. If you want to know how many bits more bits are required, so 10 bits are required, which can access B0 to B9. Okay, 1 kilobyte of memory. Now 256K, if you want to access, how many bits are required? You know that 0 to 255 is 2 to the power 8, which is also again a very standard thing which you should remember. 2 to the power is 256, 2 to the power 10 is 1024. So these two numbers and the values, if you remember, 10 bits are required for 1 kilobyte. Then in that case, another 256 locations, which will take 8 bits of 8-bit more. So totally 10 bits here, 8 bits here, 18 bits is the width of the address bus. Okay, that has to be first understood first. Now let us see. So the main memory size is this. Then the address bits are 18 bits wide, B0 to B17, and 18 bits wide it is. Okay. Now this 18 bits, how do you divide them into what sizes? That is what is to be understood from the question here. So 256 kilo of main memory, it has 8 kilobytes of direct mapped cache. So 8 kilobyte of cache, 8 kilobyte. Again, it is a multiple of 1 kilobyte. 1 kilobyte is 10 bits. Okay. And if you want to address everything in the cache, you need 3 more bits to access. So 13 bits are required. Okay, to access the entire cache. Okay. Now we are having a direct mapped cache with a 64 bytes per block. Now this block offset number of bits required is based on the block size. Okay, because once you get the entire block, you are going to be modifying only this address bits to access the bytes within the block. So if the block size is of 64 bytes, it is, if you don't know how to get the number of bits, 8 bytes or 8 locations, you need 3 bits, right? 2 to the power 3 is 8. Now 16, 32, 64. This needs 4 bits, this needs 5 bits, this is 66 bits. So that you need 6 bits of offset to access within the block. So this 6 is got from here, and then you have 1 kilobyte of entire cache, and each of them are having the block. So totally, if you add up, it is the block size plus the total number of blocks will be giving you the cache size, right? So it is 13 bits. So we know that block size is 8 kilobytes. So it is 13 bits. So if you come from the right, then you will know that 7 will be required for block index. And then the remaining bits, anyway, you calculated that it is totally 18 bits are there. So 13 bits are gone here. That means 7 plus 3. Okay. And then we have remaining 5 bits will be the tag. Tag is to say that the remaining addresses are accessed from the cache by holding the higher order 5 bits in the of the address in the tag. Okay, this has been explained in the previous video. So this explanation is only to understand from the given question how to derive the different number of bits. You need to practice with the various addresses and the block sizes and cache sizes. And if it is a direct mapped cache, okay, and it says that we have generated a ABCC, okay, as an address. So what do you do? You know, it is all hexadecimal. So write down all those individual binary representation of those addresses. And then once you are clear with the bit separation of the tag and offset and block index, then I have colored it separately. Those bits you have to separate out and group them separately. Then you will know that this block index is in decimal is 47. And which block is being accessed is the question. Cache block number in decimal to which address maps to. It is a 47. So I hope this explanation is clear. I don't want to take too much of time in explaining this answer. You should be able to make sense of it based referring to the previous explanations of direct mapped caches and this, so that you will be able to answer this question. Okay, I think with this, the CIE1 answers are discussed at length. See you. Bye-bye.